All right. Let's go ahead and get started. Did anybody do anything fun this weekend?
Yeah, I went and got coffee with a friend.
Nice. That's awesome. Coffee shop here?
And not at school.
Are you just in Huntsville area?
Huntsville, yeah.
Cool. Which one?
I forget.
That's right.
But the coffee was like much coffee I had.
Well, you can't forget. You can't say that if you say you forget.
She picked the place.
Okay. Well, if you figure out, let me know. Cabin and hiking in Chattanooga, says Phoenix. Oh man, that's awesome. That sounds absolutely perfect. Yes, this upcoming weekend, I'm going out to Colorado to do the same thing. So, yeah, I'm very excited. Yes, 20-hour drive each way. But, sorry. No, driving's more convenient. Plus, I don't want COVID. I am recording ACE. Sorry, you got beaten to it. Anybody else do anything fun? Worked at Target. Well, earning a paycheck is fun. Yeah, waiting for the paycheck's not. All right, so what did we learn last time? We did learn the chi-square, represented like that, Greek letter chi. And what do we learn about the chi-square? It measures frequencies. Caleb, yes. There's a chance it's already on YouTube, and I forgot to put it under the right playlist, but I will double check after this. If you could just shoot me an email to remind me to check that after this so I don't forget in the middle of the lecture, that'd be awesome. Thank you. Yeah, so chi-square is used when measuring frequencies. Can somebody give me an example of a type of research question that would do that? Yeah, so people's favorite cars, right? And so let's say we had Toyota, we had Honda, we had Ford, we had Chevy, and then we had Chrysler, and then let's say we threw in Lamborghini there. Right, now we're gonna ask people what their favorite car is, and we're gonna get the number of people, so that frequency, that respond to each one of these, right? So 13, 14, 2, 9, 3, 400. Right? So we can run a chi-square and see, is there a difference between people based off of what car they like? And that's what type of test? Goodness of fit or test for independence? Goodness of fit, yes. So test for independence is when you've got a second variable, right? And so if we had just the cars, that would be a goodness of fit. If we had, let's say we wanted to look at, so models would be, you could add models in there, absolutely. But you get a little bit washed out there. I think a better example would be like if we had UAH versus UAB, right? So we've got a different group on this axis, right? Yeah, and so you absolutely still could do the models, but it's a little tough because you're not comparing the same models, right? I mean, you could have in theory low-end versus high-end cars, right? But it's not necessarily the case that you know, the high-end Honda is the same as the high-end Lamborghini and whatnot. So, but yeah, so if we thought about a distinction between UAH and UAB here, we can take a look at what those values would be. We get values for each one of these. And now we can see if there is a difference between what cars people like as a function of what school they go to. So that would be the test of independence. Questions about what we covered last time? Yes, good. So last time I made a mistake. In the slides, it said that the test for independence degrees of freedom is R minus 1 times C minus 1. And this is true. It is R minus 1 times C minus 1. But in lecture, I said it was R minus 1 plus C minus 1. So what is in your slides is correct. What I told you was incorrect. And as a function of me teaching you the wrong thing, I'm not going to require you to do it for the exam. I don't think it would be fair if I can't remember it to have y'all do it. I'm going to try to take off the sweater here without taking off the mask. But. Ta-da! Where's magic shirt cover? All right. So, yes, if you're getting the degrees of freedom for the test of independence, you get the number of rows minus 1 times the number of columns minus 1. So, with our example here below, what would be our degrees of freedom?
Is that last one the color?
No, that's the Lamborghinis.
Before, right?
It would be 5. So we have 2 rows. So 2 minus 1 times we have 6 columns. 1, 2, 3, 4, 5, 6.
I don't know if it was a 6.
Yeah. And so we have 1 times 5, which equals 5. Perfect. Thanks for bringing that up, Sam. Any other questions about last lecture? Awesome. All right. Here is your fun fact of the day. After losing, I should be losing, not loosing. After losing a drunken poker bet in 2009, a New Zealand man had his name legally changed to Full Metal Havoc, more sexy and intelligent than Spock and all the superheroes combined with Frost Nova. So, and I thought my last name sucked. All right, so today we're going to be talking about the binomial test, which is going to have parallels you will have seen throughout the semester. But it's for data which is binomial, right? So having exactly 2 distinct categories. You can change your name to that, Ace. I'm going to call that bluff. Again, binomial exists when the procedure classifies individuals into 2 distinct categories. All right, so handedness would be an example of binomial data. Left-handed versus right-handed. I'm not convinced anybody's truly ambidextrous. I think there are gradations in that. But I think left-handed versus right-handed. We're going to throw out anybody who truly thinks they're ambidextrous. Is anybody in here ambidextrous? No. I broke my collarbone in high school, and I'm right-handed. I broke my right collarbone. So I had to learn how to do everything with my left hand. And even after months of doing everything with my left hand, I still sucked at it. So
I feel like anyone could be ambidextrous if like they practice, because I consider myself kind of, but like if you just practice writing the alphabet with your non-dominant hand, then like boom, you know what I mean? There you go. You're ambidextrous.
oh, that's a very hopeful message. I disagree with you on principle, but it's a very hopeful message.
Not to say that you should do that, but you could.
Anybody who takes the stats final with their non-dominant hand gets an automatic A. That's a joke. Nobody hold me to that. That was a joke. All right. So traditionally, the 2 categories are identified as A and B, right? When we're just putting in that nomenclature. And we represent those proportions of the population as P per n A. We're going to call that P. And P per n B, and we're going to call that Q. All right, so the probability of A we denote as P. The probability of B we denote as Q. The null hypothesis specifies the values of P and Q for the population. So if you flip a coin, you would expect that if that is a truly unbiased coin, 50% of the time it should come up heads, 50% of the time it should come up tails. And so we can plot what that distribution would look like as a function of, let's just say, the number of heads when you flip a coin 4 times. All right, there is a, what is it, 0.0625 chance that all 4 come up heads, or all 4 come up tails. And then you can see the graded probabilities. So there's about 1/4% chance, 1/4 of a chance, not 1/4%, 25% chance that you only get 1 heads. There is a separate 25% chance that you get 3 heads. And then, a little over 1/3 of the time, when you flip a coin 4 times, you'll get an even distribution. All right, because you all are good statisticians at this point in the semester, you know that you can't simply say, okay, there is a difference between what we expected and what we observed, and therefore this must be a bias in the ground state, the ground truth of this coin, right? Because there is still a probability that all 4 come up heads, right? So we need to know how many times do we have to flip it before we can say with reasonable certainty that this is a biased coin. Is 4 sufficient? Well, it's getting close to that 0.05 that we talked about, but not quite. And so what we're going to be doing today is tying back together a bunch of concepts, including going back to the z-scores. So the sample data for the binomial test consists of a sample of n individuals, each of whom is classified in category A or B, right? So binomial, bi meaning 2. You can only have 2 categories. The sample statistic, X, is simply the number of individuals classified in category A. What's that? No, because what is not A is just by default B, right? And so this is only important insofar as we'll be calculating it in just a minute. So the logic underlying that binomial test is identical to the logic we used for the z-score and the t-statistic all those many weeks ago. So this test statistic is going to compare the sample data with that hypothesized value, just like we did with the z-score, one sample t-test early on. If the data are consistent with that hypothesis, we're going to conclude that that hypothesis is reasonable. However, as we've done all semester, if there is a sufficiently large discrepancy between the data and that hypothesis, we're going to reject that null hypothesis. All right, we have an intuition. If I were to flip a coin 100 times and it came up heads 75 of those times, our intuition says, yeah, that coin's probably weighted, probably biased. But we need to say, what is the probability that that would happen given a truly unbiased coin?
So you would never reject the regular coin?
I'm sorry, one more time?
So you would never reject the regular coin?
So you would, you just, so as with when we did z-scores, remember, and with the p-values, we have a set criterion that we're going to establish, right? The set probability. Usually we use 0.05, right? So we want less than a 5% chance that that would have happened just by chance, right? And so there's a number of coin flips wherein we exceed that probability in the extreme. And so if we flip a coin 10 times and it comes up head all 10, I don't know the exact probability, but that's probably a 1% chance event. We would say that we have sufficient data to suggest that this is such a low probability event, if that coin was unbiased, that we have to kind of reject that hypothesis and say this coin is probably biased. Does that make sense? Good. So again, thinking about the probability of these data, we start getting into a normal distribution. And the more observations we have, the distinctly smaller probability of an event happening. Right? It's not impossible for an unbiased coin to come up heads 100 times in a row, but it is such a sufficiently small probability that it's kind of functionally impossible, right? Could still happen, but if it does happen, we're much more likely to say, okay, the root cause of this is probably it's a biased coin, rather than, a 1 in a trillion event or whatever that probability would be. So when the values of Pn and Qn, so P is that probability of A, Q is that probability of B, and N is the number of participants. So when the probability of A times the number of participants and the probability of B times the number of participants is greater than or equal to 10, you see that the binomial distribution is approximately normal. with a mean represented by the probability of A times N. So Pn is how we represent that. And a standard deviation of the square root, and again, the signifier continues all the way across, of N, so the number of participants, times the probability of A, times the probability of B. So in this case, the binomial test can be conducted by transforming that X value from the sample into the Z-score and then using the unit normal table to determine the critical values. All right, so that unit normal table was that first table we went over this semester, those Z-scores. So the equation I'm about to show you and the example we're about to do will result in a Z-score that will allow us to look up the probability of that event occurring. And this last bullet point is a little less relevant for you all in this class, but you should know that if that Z-score is slightly into that critical region, right? Let's say that that came up at exactly a probability or Z-score, which corresponds to a probability of 0.05. You would want to check the real limits for that X value, right? So that X value is the probability of A times N, or excuse me, the X value is the observed for A. So if we observed 25 participants, the real limits would be 24.5 to 25.49. And make sure that that entire score is beyond the critical boundary before we say we're going to reject the null hypothesis. All right, what questions do we have so far? Nothing, everybody.
I have a question about the P and Q. I was thinking about how to figure out which variable is P and which variable would be Q. Would Q just be the unfocused on variable, or the variable that we don't focus on? Like,
Yeah, so I mean,
just because for the mean we have to use P, but like what keeps us from using Q to like find the mean? You know what I mean?
nothing, it's just standard procedure to keep it consistent, right? So, I mean, P is just the inverse of Q, right? So what is not P is Q, and so you could essentially assign whatever you wanted, right? So heads could be P or tails could be P, at which point you're functionally also using Q in that circumstance. But it's just standard procedure to rely on whatever your assignment is to use P. So that's a good question.
Okay, thanks.
It won't give you different probability. It'll just, yep.
Okay, thank you.
Yep. All right. So from Psych 100, you may remember hearing about this study that wanted to see if kids had kind of an ingrained understanding of heights, right? And the dangers associated with heights. So what they would do is put a kid on a box in the middle of two drop-offs. Now, the drop-offs were covered by like clear Lexan or polyacrylic glass, things like that. So they couldn't actually fall. But then they would have the baby crawl around and see what happened. Would that baby willingly crawl towards that deep side, that high side where there was potential risk? Would they crawl to that shallow side? Or would it be just kind of equal, right? So for this theory, we would say if there is an ingrained apprehension against heights, we would expect the kids to move more towards that shallow side than the deep side. If we see no difference between these, we would say, well, there's probably not that ingrained, and it has to be something that's learned over time. And so our null hypothesis in this case is that the probability of moving to the deep side is equal to the probability of moving to that shallow side. So P and Q are both equal to 1/2, right? Equal probabilities. And let's say we collected data from 27 kids. So if P is 0.5 and Q is 0.5, right? These are both representing that 1/2 probability. And we're multiplying it by N, which is 27. Our null hypothesis puts it at 13.5 kids in each direction. So 27 is the number of kids that we observed.
Wait, where did you get the 0.5 from? I'm sorry.
Yeah, no, good question. So the 0.5 comes from the equal probability, right? And so our null hypothesis is saying that kids are just as likely to move to the deep side as the shallow side, right? So we're saying that the null hypothesis is there's no ingrained difference in what the kids will do. And so just they should be as equally likely to go to the shallow side as they are to the deep side. You can think of it as a coin. They would be equally as likely to flip a head as they were a tail. Does that make sense?
Yes. So that came from 1/2. The 0.5 came from that, or
Yes.
Okay.
Exactly.
I understand.
Yep. Cool. All right. So let's say we conducted that experiment. We saw that 3 kids went to that deep side, but 24 kids stayed crawling towards that shallow side. So now we want to establish what is the probability that that would happen if there was not some force at play. Right? If there was not some reason that the kids were choosing the shallow side, what's the likelihood that the kids, 24 of those 27 kids would go to that shallow side? And so we once again bust out the z-score. And to find that z-score, we take our x value, in this case A, minus Pn. So our observed value minus that expected value divided by the square root of the number of observations times the probability of A occurring, which is crawling to the deep side. Sounds like an indie rock band name, Crawling to the Deep Side. I like it. I'm not your guy for being in a band, but I'll come cheer you all on. Times Q, which is the probability of B happening. So if we were to put all of this into that equation, what would that look like? What is our x value?
3.
3, exactly. So 3 minus the probability of A times N, all right? And we've got that up here already, so that's 13.5. There we go. Divided by the square root of what's our N? 27, exactly. Times, what's P? 1/2, exactly. 4.5 times, what's Q?
0.5.
1/2 again, exactly. Yes, perfect. So, when we put all of that in, we get 13 minus 13.5 divided by the square root of 27 times 0.5 times 0.5 gives us negative 4.04. And so if we look that up in the back of the book, you'll see that a z-score of 4.04 corresponds to something like 3/1000% chance that this would happen just by chance. Right? So we can feel pretty confident in saying there's probably a reason that the kids went to the shallow side. Right? So we've rejected the null hypothesis, and now we have evidence for our alternative hypothesis. And our alternative hypothesis is that there must be some sort of ingrained apprehension towards heights. Questions about that?
I got like 15.5.
You got 15.5? So
40.5 on top, right?
no, so on top would be negative 10.5. So 3 minus 13.5.
Oh, I thought it was 3 times 13.5.
Nope.
That's great.
There you go. That's fixed. Yes. Yep. So you have you would get the same if you used Q instead of A, right? So if this were now 24 minus 13.5, you would have 10.5 rather than negative 10.5 on the top. So the probability comes out to be the same. You just ignore one of them because it's a binomial. If it's not one, it's the other. Make sense? Yeah, cool.
Okay, so you're rejecting it because why?
So if you look that up in the back of the book, and I just looked it up earlier when I was going over this, a z-score of 4.04 comes out to a probability of 0.0000003 or something like that.
That's with the alpha with 2 points.
So remember, with z-scores, we're not using, well, we do use 2 tails at different times, but because in this case, we're just looking at, what is that value more extreme? We're not looking at necessarily what is the cutoff at this point. If we were establishing that cutoff, then we would have to establish, okay, what is the z critical as a function of, is this a 1-directional or 2-directional test? But because we're not establishing what that cutoff is, if we first had to establish that cutoff, I'm just saying that the probability of this event is that. And so we know that regardless of what cutoff we're using for that z-score, whether it's 1.6 or a 1-tailed test, well beyond it. If what number was 10 or higher? Yeah, that just means if we have more than 20 participants, we treat the data as a normal distribution, which allows us to run it with these probabilities. Cool? That makes sense? No, I'm not doing sure. All right, so where'd we go? I don't remember what slide this was on. Yeah. So all this is saying is if we have more than 20 participants, we can assume that the data is normally distributed, right? Because if you only have 4 data points, let's find an area here. If you only have 4 data points, it's very possible that when you look at the frequencies, you have 3 over here, 0, 0, and 1, right? That's not normally distributed, right? And so all that's saying is with 20 people, it's very likely that we are getting a data set that is normally distributed, which allows us to use the equations we've been using in this. Does that make sense? If it doesn't make sense, let me know. Okay. All right. What other questions do we have so far?
Not directly related. Did you put this PowerPoint on Canvas yet?
This PowerPoint should be on Canvas.
Okay.
Yeah.
Okay, because my book
It is.
stopped after chi-squared, so I was just making sure.
So this is, yeah, so this is one of the appendices in your book.
Oh, okay.
Appendix, I don't remember. I think in the syllabus I indicate what appendice it is in. So, I'm sorry, Kate, you asked a question?
Okay.
Yeah, is this equation is x minus p over square root of p in PQ? Have we seen this before?
So we haven't seen this directly, but you're actually raising a good point. So a lot of what we're doing here is directly related to a couple other principles, right? And so it's similar to what, at least conceptually, what we've done throughout the semester. Well, I don't think we've seen that direct equation.
Yeah, I don't remember there being a minus sign, but I remember the denominator being familiar.
Yeah, and so the chi-square test, as you may have noticed when I was talking about this binomial test, I said it's that observed value minus that expected value over the square root of that observed, or excuse me, of that n times p times q. And so we could also have run a chi-square on this, right? Everything we talked about last time would still apply here. We could still do that chi-square. So the next logical question is, okay, how do we decide what to do for each of these tests? And the answer is chi-squared is the same thing as z squared. Mind blown. And so if you were to take your z value that you calculated and square it, you'd get a chi-squared value. Or if you were to take the square root of your chi-squared, you would get the same probability as your z-score.
So chi-squared equals z squared?
Yes. Yep.
Just make sure.
Mhm.
Oh, it's up there.
Yeah. And so one of the things you'll also notice is that in doing this probability, because you only have a degree of freedom of 1 in a binomial test, if chi-squared equals z squared, then chi-squared critical should be the same as the z-squared critical. Or said another way, chi-square critical, the square root of chi-square critical is equal to that z critical in 2 tails. And so we already previewed it, but if we got 4.04 for our z-score, or 16.33 for our chi-square here, do we reject or retain the null hypothesis? We reject the null hypothesis. Exactly. Excuse me. All right. Any questions about what we've done so far? Today, not in class. They're not equal to each other, but if you take that chi-square critical, the square root of that, you'll just get that z critical. Or if you square that z critical, you get the chi-square critical. All right. So now let's look at the sign test. So sign test is a special application of that binomial test used to evaluate the results from a repeated measures design, comparing 2 treatment conditions, and that difference score for each individual is classified as either an increase, or a plus, or a decrease, negative, where was I? And that binomial test evaluates the null hypothesis by saying the probability of an increase is equal to the probability of a decrease, which again is equal to 1/2. So what this may look like, let's say we have 8 participants and we're going to give them a coronavirus treatment. And I'm going to ask them, how do they feel? What's their subjective experience? And 7 of the 8 say they represent a decrease in the symptoms of coronavirus following that therapy. 1 participant said, actually, I feel worse. So when would you use this sign test? Well, one example is when the data have no limit. What's that line from Mean Girls? The limit does not exist, or whatever it is. So the example from the book is the sedative drug on problem-solving abilities in rats. So let's say we have a whole bunch of rats and we give them some sort of problem. Say just run through a maze and figure out where that cheese is. And we get a time for all the rats. And then we give them a sedative and a new problem. Say go find that cheese. And only about half the rats are able to find that cheese. Well, with everything we've done to this point, you couldn't say if there was a difference because you're having to throw out half the rats because they didn't finish the test, right? But after a while, you're going to say, okay, we're not going to let this rat go until they die. And so you just make a mark and you say, okay, well, they got worse. Clearly took them longer. We don't know how much longer. We can't run the typical parametric statistics with numerical values. But now we can still establish, okay, if there was a sedative effect. You could also use it for things like perceptions of improvement or worsening. So if you're struggling to actually quantify something, you could just ask a doctor to evaluate the patient and say, do they seem better or worse than yesterday? Or you could ask the patient themselves, do you feel better or worse than you did yesterday? Sometimes it's hard to quantify. Right? If you've ever had the flu and you feel like crap and your parents then ask you the next day, how do you feel? You say better than yesterday, but you can't really quantify how much better. You just say better, right? So now you can be using this type of sign test to evaluate that. This is also uniquely useful when you have a couple data points way outside the norm and don't want to exclude them, but you also don't want them to have a massive effect on the test. All right, let's say I came up with a coronavirus cure, at least I thought it was a cure, and I'm going to test it. And I give it to 10 people infected with the coronavirus. And for 8 of those 10, nothing really happens. But for 2 of those 10, their symptoms go away immediately. You don't really want to exclude them because that provides some evidence that my cure seems to be working. But it may be a little misleading if I say, look, the average reduction in length of time is 3 days, when in reality, the data suggests that, okay, it either fixes you immediately or doesn't fix you at all.
So is there any chance that like you look at patients that they haven't gotten better or worse and just stay the same?
Yeah, so that is one of the downsides of using this test, is it doesn't really allow for you to do no change to that. This fits into kind of a category of tests we call 2 forced alternative choices, right? So you have to say better or worse. You can't say I'm the same. And so it is absolutely kind of a methodological flaw. That's a good question. And so we've been talking about miracle memory legume throughout the semester. And I want to see if it increases or decreases the time taken on the final exam. So I'll give you one final exam without the miracle memory legume. And then because you all love statistics, you volunteer to take another final exam again. And I look at, okay, does it increase or decrease the amount of time it takes for you on the exam? So I've got 6 participants, 5 of whom show a decrease in time. 1 shows an increase. And again, it's important to register that these increases and decreases, right, these positive or negatives, are not telling you the magnitude. It could be a 1-second decrease, or it could be a 50-minute decrease. All it's saying is it either increased the time or it decreased the time. So the probability of an increase, according to our null hypothesis, is 50%. The probability of a decrease, according to our null hypothesis, is also 50%. So in this case, our x is the decrease, right? So for the number of people for whom the time went down was 5. The number of people for whom the time went up was 1. Our n equals 6. The 6, even as crappily as it's written. And so we know p of 1/2 times 6 gives us 3. So 5 minus that pn of 3 yes.
So why are we picking 5 instead of 1? Like what, how do you determine which one to use?
Doesn't matter, I'll give you the same probability.
You will?
Yep. I think I screwed up the denominator here. So, yes, so that should be 6. Your n times q. So 6 times 1/2 times 1/2. And this number will be slightly different. It's 6 instead of 5. But you get a z-score of, we'll say, 1.79. So in this case, what do I say? What is my research conclusion? Yeah, you reject the null hypothesis. And because this is a binomial test, we know rejecting the null hypothesis, we can just go back and look at the data. There are more negatives than positives. So we suggest that the miracle memory legume decreases the amount of time it takes people on the final exam. Amber says, are the arrows indicating increase? Yes, yes, it decreased.
It's now 1.63. Does it make a difference because it's less than the secret?
Yes, so when you actually put that in, 1.63. So now, what do? Do we reject or fail to reject? Oh, can y'all hear me now? Hello? Hello? Okay. If I cut in and out, but we're just about done here.
I do have a question.
So we
about-
fail to reject with the z-score based off of the correct cells.
I have a question, and this might seem dumb, but how did you
Yeah,
find this secret? Was that in the back of the book, or did you get it from the example that you just provided us, or like how did you get that? Because I see it on every slide. So is it in
Sorry.
the back?
You kind of cut out. Did you say? Yeah. You kind of cut out. Did you ask how did I get that z critical?
Yes, I did. I did ask because don't we need it? We need that for this
Okay.
exam, right?
Yes. Yeah, so just as with the beginning of the semester, we have to establish what is that probability that we're interested in. And frequently, with doing that probability, we're going to set a probability of 0.05. And so that z critical is looked up in that back of the book of what is the critical value for z, which corresponds to a probability of 0.05. And in this case, we stacked the deck in my favor and made it a one-tail test. But that z critical is found in the unit table in the back of the book. So we initially rejected it, but once I put in the correct number, that number actually changed. And so we get 1.63. So now we fail to reject the null. Excuse me.
So we're comparing that number.
So my claims. Mm-hmm.
So we're comparing the
Yes.
1.3.
Yes. So that one.
Sorry.
Yes. Value of 1.65.
Okay, I understand. Thank you.
I'm sorry. What'd you say?
If the Z and the Z critical are equal, do we still retain it? Or is that?
I would be inclined to reject it because you're saying that is a 0.05 probability event. So if you're establishing that 0.05 is a sufficient level, then getting something at 0.05, I would reject. That being said, when you're doing this on a computer, the likelihood that you get exactly 0.050 is so minuscule because it usually carries out to like the 100th point or whatnot. And so if calculating it by hand, you get the same thing, just reject the null. But besides that, just default to whatever the computer says. So Amanda says, just to clarify, for this example, did we reject or retain the null? So with this new number, this 1.63, we retain the null hypothesis. Other questions about this?
Wait, we retain it or we don't reject it? I thought we were retaining it because I thought you said
Same thing. So for the null hypothesis, yeah, for the null hypothesis, if we retain it, that's the same as not rejecting that null hypothesis. If we reject the null hypothesis, that's different. But the retaining the null and failing to reject the null are just the same thing, just different ways to say it.
okay.
Sorry, I couldn't hear you. What's that? That means it didn't work. My miracle memory lagoon claims are full of bunk. We spent the entire semester talking about something that didn't work. What's that? Not for nothing. You got the opportunity to take more stats. And what could be better than that? But yes, for purposes of evaluation, yes. So one of the cool things is what we've been covering the last 2 classes is exactly what scientists around the world are doing right now with COVID vaccines and COVID treatments, right? They're seeing if patients get better or they get worse. We're looking at frequencies. So how many people get the coronavirus after they've gotten that vaccine versus how many don't, right? So Pfizer announced last week, I think it was, that they've got a vaccine that they claim is 90% effective. So that means if you get that vaccine and are exposed directly to that coronavirus, 9 out of 10 people aren't going to get the coronavirus, right? And so at that extreme level, we can say, wow, that's really effective. But we need to know what's the probability that that would happen, right? Because some people are going to get exposed to the coronavirus and just not catch it, right? There wasn't a sufficient level of exposure. And so now we get to look at those probabilities and say, okay, is this an effective treatment? Is this an effective vaccine? Questions about anything we covered today? Cool. So one little housekeeping thing. Your SIEs are open now. These SIEs benefit y'all as students in that if there's something you really didn't like about this class, it's your second chance to let me know, besides what we did in the middle of the semester. They're also used for determinations about promotion and tenure for junior faculty like myself, right? And so getting those feedback That helps me. If you didn't like the class, that helps me improve. And if you did like the class, that helps me with the actual promotion and the receiving of tenure down the line, if I'm so lucky. So regardless of your feelings about the class, please go fill out these SIEs. They help me tremendously. And while at this point, it's unlikely that by these SIEs, I can incorporate into future classes. And if we get, what did I say in the email? I think over 2/3 of the class to do it, I'll give the entire class some extra credit. It's fully anonymous, so I can't tell who's the 2/3 that did it. But if over 2/3 of the class does the SIEs, I'll give you all some extra credit. And on Thursday on Wednesday, God, I'm already ready for the weekend, is our last lecture of the semester. We're going to be going over statistical tests for ordinal data. Your final exam will be here before you know it. The 2 classes after Thanksgiving, we're going to be doing review sessions. Those will be completely virtual, right, per university standards. But we will have those 2 class sessions to go over anything you'll have questions about. However, don't start waiting until after those to start studying. Come with specific questions about it, things you don't know. Do lots and lots and lots and lots and lots of practice. And I'm sure you all will ace the final. Feel good about it.
So you're having 2 virtual classes on class time?
Uh-huh. Yes. So this time in 2 weeks, so after Thanksgiving, we will have our first review session, and then that Wednesday we will have our second review session.
Can I ask you a question after class instead of those days, because I'm actually having to come to those? I
Sure.
didn't know we were doing that.
Yeah, that's fine.
So sorry.
No, you're fine. Awesome. All right, if there's nothing else, have a lovely rest of your Monday. It's good to see those of y'all in class for the last time until the new year.